Logarithmic differentiation is very, logarithmic differentiation is a very powerful tool to have in your arsenal. But don't get too carried away with this. Suppose I asked you to take the derivative of this, y equals x squared. Now let me show you something that's correct. You can take the log of both sides. Right? Now you take the derivative of this. 1 over y prime is 2 over x. And now y prime is y 2 over x, so y is equal to x squared. 2 over x, and I get 2x. This is correct, but why in the world would you do that, right? Just y prime is 2x. You already know that, right? So the point to my little thing is, don't use logarithmic differentiation unless there's something in it for you. Right? And there will be plenty of opportunity for that, I can tell you. So the problem that I refer to, that I said was a great missed opportunity for almost everybody, some of you got this right anyway. Number B is this: g of x is the natural log of x squared plus 1 half over e x cubed sine squared of x. Now, what pretty much everybody did is, okay, what's the first thing you come to? Log of blob, right? So log of blob is 1 over blob, and then so it's actually 1 over this huge mass. Then you have to take it and multiply by the derivative of the sheet. It's a nasty change or closure. And some did that right. It's fine. But so much easier to take one step. Use the property of logs here. I'm gonna write this again fast, but I want you to tell me if this isn't clear. It's log of this, so that's 2 log x plus log of this, which is 1 half log x squared plus 1. Now, these guys at the bottom, minus log of e to the x cubed. So that's actually x cubed log e, but log e is 1. So actually, it's x cubed minus 2, because it's sine x squared. So I use the property of log. This is one way to write this function. Here's another way. This is much easier to take the derivative. This is 2 over x plus 1 half 1 over x squared plus 1. 1 over this times the derivative of what's inside minus 3x squared minus 2 times 1 over sine x times the derivative of sine x, which is close. There you go. So you let this in this huge, nasty fraction form. If you don't have much of a social life and time on your hands, you can sit there and mess around with that fraction. You actually everybody see that. Okay, so we got into the next section a little bit last time. The whole idea behind this section, inverse trig functions and some others, logarithmic differentiation and implicit differentiation, these are all good in helping us understand inverse functions. Now, there's something that should bother you when I say inverse trig function, right? Does anybody remember what you need what property a function needs to have for it to have an inverse. Right, it has to be one-to-one, it has to work on line, because otherwise, if you flip it over line like glass, it's no longer a function. And this bothers me a little bit because, for example, like cosine x and y tangent x, these things look like this. I don't know much, but I do know that they're not one-to-one. These, all of these very much fail the horizontal line test, right? In fact, a horizontal line between y equals one and y equals minus one likely to be significant. So, what's this business about inverse functions, right? How do you do this? Well, here's what happens with the inverse functions. Notice one of the important things about the trig functions is they're periodic, right? They, does everybody know what periodic means? Well, that's right. They all repeat themselves over and over, right? That's so you can forget about if you understand sine from here to here. That's all you really need to do to understand sine. You know it, but because this piece just this kind of flipped over and then everything was. What about cosine? Well, actually, notice this is from what? Minus pi over 2 to pi over 2. Right. That red bit does satisfy the horizontal line test. And it's really all the information I need to know because if I understand the red bit, I can translate and get all the sign. So that's actually good enough. It's not like this does different things. Now, minus pi over 2 to pi over 2 will not work for cosine because look at cosine minus pi over 2 to pi over 2. It's not one-to-one, right? But, well, cosine we've got to change a little bit. Notice if we know cosine on this interval from 0 to pi, then we know it everywhere, right? Because for example, this bit right here is just this thing reflected back over the y-axis and then right. And so notice we don't consider all of sine, we consider it on the range minus power 2 to power 2, which is a range big enough for us to get all the information we need about sine, but small enough so that it's one-to-one. Cosine, same deal. Big enough to understand all of cosine, but small enough so that it's one-to-one. And tangent, I've always thought was the most obvious, right? Because tangent's just a copy job of this thing between two vertical axes, right? So let's just forget about tangent everywhere except in the middle. And this is also, this is like sine. Now, the inverse functions of these are what you get when you flip this, you flip it around the line y equal s, right? Inverse sine, inverse cosine, inverse tangent, for example. of this. The tangent function itself has two vertical aspects, right? Minus power two and power two. In the domain of the zero. So when we, if I were to reflect this around the line y over line y equal x, what would those two vertical asymptotes turn into? Horizontal. So what's going to happen here is this is going to be power two minus power two. And the inverse tangent function is this. The inverse tangent function is interesting because the inverse tangent function actually has the domain all the reals. You can put any number into your calculator and it will return an inverse tangent function, and it will, your calculator will always return it minus power two, not including the inverse. The inverse cosine function will always return something between 0 and pi, and the inverse sine function will always return something between minus power two, even though not all angles are between 0 and pi, and not all angles are between minus power two. Okay. Everybody, you've all seen the inverse trig functions. Right? So this hopefully a little bit of a review. So what are the derivatives? Well, actually, the whole notion of implicit differentiation is very good at figuring out derivatives of inverse functions if you happen to know the derivative of the function perfectly. So suppose that I have y equals inverse sine of x, and I want to well, of course, I've got no idea what the derivative of the inverse sine is, but on the domain of this, I can take the sine of both sides, and the sine of the inverse sine of x, just x, as long as we're on the domain of the inverse sine. Everybody okay with that? That's the whole meaning of an inverse function, is it's a reverse gear. Y is inverse sine x, as long as x is sine y, as long as you're on the appropriate domain defined for this. Now, I have no idea what the derivative of inverse sine is, but I do know the derivative of sine. So if I were to differentiate this implicitly, of course, the derivative of this side is 1. What's the derivative of sine of y? So I get y prime when it goes on y. So in a certain sense, this is the answer to my question, right? But it's very unsatisfying because I started out my project in my book. I wanted to find the derivative of inverse sine of x. I wanted to find y prime, and I got it, but it's in terms of y, which is it. Anybody see it? Right, the old trick that we need. I usually go back to this equation, but see, here's the thing. I've got a cosine, and this one's what we said about sine. Does anybody know a fundamental theorem in trigonometry that relates cosine and sine? There's an equation. What happens if you square sine and add it to square the cosine? Okay, good. So let's see what that thing. Yeah, sine squared. That's cosine squared. Now, if I were to solve and cosine y. Now I'm going a little bit fast and loose here because really go from this step to this step, square root, and I need to be careful that what I get is the positive square root. But in this case, we're okay. So I invite you to check that. And this. Look at this equation here. Sine of y is equal to x. So this, I can divide 1/6 squared. So this is derivative of, so in summary, d dx of the inverse sine of x is this. Okay, so let's find the derivative of the inverse cosine. It's almost exactly like this, in fact, there's only one little subtle difference. Suppose y is I'm gonna go through kind of the same exercise here. I've got no idea how to deal with the inverse cosine, that's the whole point of this. But I can deal with its inverse function, which is cosine, that's an old one. So if I take the derivative of this. Derivative of cosine is negative sine y. It's y prime. 1. So I get y prime is minus 1 over sine y. Now notice this equation is kind of symmetric. Notice that sine y is the square root of 1 minus cosine squared y, which is the square root of 1 minus x squared. So this is minus 1 over the square root. Y'all see the first instruction. Notice the derivative of the inverse sine of the inverse cosine. Opposite of something. Okay. So notice what happens if you take the derivative of the inverse sine of x. See this. Right, explain this. Let me ask you this. So you took the derivative of this thing. This is a function and you got zero. What kind of function, what's the easiest kind of function you can think of as a derivative? You get zero? Anybody give me any function? Take derivative of zero. Or any constant will work, right? So with that in mind, can somebody explain this to me? Let me just draw a triangle. Let me draw a right triangle. Or a second triangle. Uh, so. Anybody tell me what sign that is? I'm sorry. Right, the sine is B over C. And the cosine is X. So so now we're kind of familiar, I'll start with this. Right, the inverse sine of B over C. Stay. What is? So now I'm gonna, what about the inverse cosine? Now, of course, the inverse cosine of A over C is theta. What's the inverse cosine of B over C? All this angle, right? Because if I stand and look at this right triangle here, it looks like B over C is the cosine of this other funny Greek letter, right? So what is then the inverse sine of B over C? What's the inverse cosine of B over C? It is the angle theta, which is in this corner, plus the angle phi, which is in this corner. What do those two angles always add up to? It doesn't matter, yeah, it doesn't matter, what theta, these are individually, they always add up. Because the three angles have to add up pi, and this is a right triangle. So these two have to all of them. This could be big or small, but the sum of those two always is pi. So notice in this case, the inverse sine of this plus the inverse cosine of the same thing is always power two. So no wonder I got zero derivative, because this thing is just, I took the derivative power two. Okay, any questions? All righty. One more. Okay, how about the inverse tangent? We talked about this one yesterday. but I was not turning in. Suppose you have y inverse tangent x. What you want to do is you want to find y prime. Well, let's put it test here. Take the derivative of tangent y. This is secant squared y prime. So I get y prime is 1 over secant squared. And the identity that I invoked last time turns out that secant squared y is always tangent squared y plus 1. This is basically cosine squared cosine squared 1 divided by cosine squared. And this is 1 over squared. So and I'm going to focus on these three really because they're kind of universal and common sense. I'll explain that in a moment. The other three inverse trig functions, they exist. There's an inverse cosecant, an inverse secant, an inverse cotangent, inverse cotangents. So, okay. Well, let me, let's do some. So, example. Suppose I ask you to take the derivative of the inverse tangent of e to the sine of x squared. Well, all we've got is a new tool in our repertoire. These rules say, for example, the derivative of inverse tangent of blah is 1 over 1 plus blah squared. Okay. So let's get this party started here. This is 1 over 1 plus the square there you go. That's my first step. Any questions on where that one came? Okay, now we just trickle down. So we've gone inside the first thing. The next thing I come to is e to the blah. What's the derivative of e to the blah? E to the blah. And the next thing I come to is sine of blah. What's the derivative of sine? Cosine of blah. And finally, I go inside that last parentheses, derivative of x squared. Right, and I think I've shared with most of you this, at least, but when I ask you to take a derivative, like I did here, be done with it now. Done all the calculations, done the chain rule, derivative, done. Don't sit here and waste your precious time trying to simplify. You should only simplify something if there's something in it for you. So for example, if I had a part B to this and said, where's the tangent line 0, then it might help you simplify it a little bit so you can figure that out. But just follow the instructions. Don't do more. Okay. This, I'm not. Through this, well, first part of my rule, like this, this tells me that the derivative of the inverse sine of blob is 1 over the square root of the square root of 1 minus whatever this blob is. Step 1. Everybody okay with this? Okay. Chain rule. What's the next thing you have to say? Derivative of what I'm inside, in this case, is log blob, right? What's the derivative of log blob? Oh, now what? Good. There you go. Let me give you, and I'm going to just kind of regurgitate. I'm gonna go through this carefully. Um, so here's the derivative of inverse trig functions according to the book. And I'll tell you what I mean by that. Rather start with a comment at the moment. Okay. Derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. For x between minus 1 and 1. Why do I have this subscription? Because actually, the inverse sine function is only defined between minus 1. Right? Maybe you've done this experiment before. What happens if you put a 2 in your calculator and press the inverse sine function? What will happen? It'll give you an error because it's not even defined. There is no angle that has sine of 2 because the sine of any angle is between minus 1. So the domain, the inverse sine has to be, same with the inverse cosine. However, the inverse tangent, the inverse cotangent, they put anything. Now the other two, I de-emphasize a little bit because depending on the book you read, you might get different answers. So here is, according to the way Briggs Books does it, it is derivative of inverse secant is one over the absolute value of x times the square root of x squared minus one. And this is the absolute value of x is equal to one. By the way, in all these, it has to be strictly bigger, and notice right here what happens. The inverse sine function is defined at one, but the derivative is not. If you try to plug in one and minus one. Here, for example, the cosine has output between minus one and one. The secant is the reciprocal of that, and that's why the absolute value of x has to be bigger than one. And dx cosecant, the inverse cosecant of x, is minus one over the absolute value of x square root of x squared minus one. Absolute value. Now, how many of you have ever seen this? Well, if you go look, for example, in the Stewart calculus book, which is kind of very popular, maybe the majority of universities, Stewart formula has no absolute value. Yet the Briggs formula has an absolute. Which one I'm doing? Which one I'm doing? Actually, they're both. The difference is this. Let me draw you, for example, picture the secant. Notice the cosine is zero, isn't it, at power 2 minus power 2 like this. Right? So the secant actually has vertical asymptotes. So often. And it actually looks something like this. Um, now notice the secant isn't a one-to-one function either, is it? So how do you pick a one-to-one piece that reflects this? Well, some books might pick it here. Notice just that if you ignore all the black stuff, just look at the red stuff, right? That's a one-to-one piece that reflects it. Right? Well, some books pick it this way, and some books pick it a different way. They pick it this way and then down here. They pick other branches of this. And the problem is when you pick the representative from the inverse function, you pick this, or for example, you could pick this, it'll give you a different answer, right? Unfortunately. And the choices for picking this are pretty much established and uniform when it comes to the inverse cosine and the inverse sine. Everybody agrees on the pick and the inverse tangent. But for the inverse cosecant and the inverse secant, if you look at different books, you'll see some where you get this formula for the derivative of the inverse secant, the inverse cosecant. You'll see some with no absolute value, but they pick the two bread parts to make it work differently so that they don't get an absolute value. And unfortunately, it depends on, what your definition is in the first place. That's why I don't care that much about secant and so forth. you can get most of your work done with the inverse. So. Okay, any questions? So that's culture. But you all should focus mostly on knowing these inverse trig functions for the inverse cosine, sine, and tangent. Here is kind of a general thing about the inverse function. So let me draw it on that. I'm gonna try to make this easy. So if you have a function, um, if this is y equals f of x, please forgive what word draw. Uh, Okay, this is what y. Are you all familiar with this when you first talk about inverse function? Basically, if you have a one-to-one function, like I tried to draw this black function, if you reflect it about the line y equal x, you get what the inverse function. So here's my question. So I ask you to use your Jedi instincts here. If I have, let's say, a point on the original function here, I have a tangent line here, then there's a corresponding point here, right? Just reflection point, reflected about my x. Not have a tangent line here. Anybody want to guess what the relationship between this slope and this slope? Can you be more specific? What do you mean by opposite? There you go. It should be the reciprocal, right? If you think about this, here's kind of the, if this were absolutely horizontal, the flip point should be absolutely vertical. Right? So I'm thinking that these two should be reciprocal. So in other words, if this is the point AB, by the way, this means FA. This point is on the original function. What's the corresponding point on the inverse function? Good, good, good. So the other point is BA because this means that F inverse B is equal to A. And that's what inverse functions do. So here is a theorem that goes in lockstep, and then I'll give you kind of a practical problem. And actually, I'm going to show you what this is. Suppose that f x differential. Let's just be got I'll take the derivative and it's defined. And has inverse function on some interval I. So for example, this black function here is differentiable, looks like, and has an inverse function on this interval I. If for some x zero in I, some point in the interval, if f prime of x zero is not zero, then g of x was that inverse of x is differential. At y zero, and f inverse prime of y zero, which is g prime of y zero is 1 over f. I'm going to show you why this is true. Let me interpret this narrative for you. Okay, here's the situation. Suppose you have a function, and suppose it's different. Okay, it just means I can put the derivative. Suppose it's got an inverse function on some interval. Well, that just means it's 1-to-1, right? So, for example, if you look at this picture here, on this interval here, my black function looks like I can take its derivative. And it's 1-to-1, so it's got an inverse. In fact, I've drawn the red inverse. Right? Now, suppose that some x zero in here, the derivative is not zero. Would you agree? I mean, it looks like the derivative is pretty close to zero, but it's not zero. It's slightly going up. Everybody agree with that? So suppose that the derivative of the original function here is not zero, then the inverse function, the red function, is also differentiable at the mirror point. That's what it says. If the function here is differentiable and it's not zero, then the mirror point right here, the BA, see, y is f zero, x zero, so f x zero is f a. Then the red function is differentiable at the mirror image point, and the slope of the tangent at that point is the reciprocal of the slope of the tangent at the original. That's all this says. Why do you suppose that we made that demand that f prime of zero is not zero? Why is that? Why would the lawyer put that there? That's exactly right. It's because right here, if you're in Jim's world of pain, if that's a zero, right? And that's it, right? So, by the way, what would happen if the derivative is zero? What would you expect to happen at the mirror image point? No, it would be undefined. I would expect there to be, for example, a vertical tangent. So, and in fact, I'll give you an example where this happens. Like, let's do this all. What's the derivative? So what's the slope of the tangent of the origin? Zero. What's the inverse function? Y equal x cubed. Think about this. If you cube something and then you want to undo it, what do you got to do to undo it? Take the cube root, right? That's the input function. What was in the first year? So what is this section? Notice what happens at zero. Notice that the derivative of the inverse function of zero is undefined. The original function is zero derivative. The inverse function has undefined derivative, zero. And if you look, you can see that in fact the y-axis is a vertical tangent. But okay. So why is this true? Why is this theorem true? Well, let me go through this. I'm not going to put in all the details. I'll be a little bit fast and loose, but I want to give you kind of the gist of why this is true. So if you look at I don't like this inverse notation doing derivatives. If you look at g prime of y0, which is what we're looking at, I'm going to go back to my roots, like REM on the Monster album. And what is this? This is the limit as y goes to y0. This is actually the definition of derivative. G of y, G of y0, y. This is the definition of the derivative, right? Y gets close to y0. This is the limit of the secant slopes, right? Well, we can assume that y is very, very close to y0. That's what this limit thing is all about. And notice that g of y0 is x0 because f of x0 is y0. We define it this way. And of course, g of y is x, call it x. And as x goes to x0, f of x goes to f of x0. Because in fact, f is differentiable, and so it's continuous as well. So if we kind of pick up where we left off, this is equal to limit. Well, see, g of y is x. G of y0 is x0. Y is f of x. Just using the inverse function. And y0 is f of x0. Now, I did say limit as y goes to y0, but now I've got nothing but x's in here. And as y goes to y0, x is going to x0 because of the continuity. And this is limit as x goes to x0 of 1 over f of x minus f of x0 over x minus x0. Just manipulating the fraction. And this is 1 over f prime of x0, which is exactly what we predicted. Okay. Let me go through and then I'm going to start talking about related rates. Example. Here's an example. This is the kind of question I may ask you. Um. Yeah. So let's let that. Consider this particular function. Um, let me ask y'all something. What is the domain of this function? What values of X can you plug into this and everything's there? Everything, absolutely. This is a polynomial, it's continuous everywhere. So its domain is all the reals, it's continuous everywhere, it's differentiable. And in fact, what's the derivative? Okay, good. I also claim, now here's one that you might have to scratch your noggin a little bit about. I claim this function is also one. So in particular, it has an inverse. Anybody? Yeah, but so does cosine x. Oh, okay. Look at this derivative. Right? Let me ask you this. What's the smallest derivative? What's the smallest you could ever make that derivative? Well, right, yeah. Get a zero out of this, or one for a grand total, right? Great. So this means, this is speaking to me a little bit. It's telling me that when I draw this function, the slope of the tangent line is going to be one or more everywhere. What do you think such a function like looks like? It's what explains to me why such a function has to pass the horizontal like this. We actually haven't had this theory, but I'm feeling a little bit to your intuition. If this function didn't pass the horizontal line test, it would have to be 2 points on the function that you could draw a horizontal line. Right? So let's suppose you hit the point on the left first. How you gonna get here? Slope of the tangent is always at least one. I mean, you can't go back this way because now your slope of the tangent is negative. And if you go beyond that, then you can never draw that. So this is the kind of theorem that we're going to get to, but does everybody kind of intuitively see? While this thing is sort of always going up, it has to. So, and if it's always going up, and it's continuous, then it passes the horizontal line test. Let me ask you a question. I can think of a function that's always going up, but fails the horizontal. Always, it's always increasing. But it fails the horizontal. It almost fails the horizontal line test, but it doesn't quite, right? Because I know what you're saying. It's flat there in the middle, but no horizontal line will hit that one. Think a trig function. And when you see the solution, you'll see that I'm not. But see, it's not always going up because it's got like curve like this, pretty close. So. At every point on this thing, the tangent line is positive. It's always good. How did I get away with this? Of course, it fails the horizontal line. It's very bad. What is it about this that allows me to pull this cheap? It's not continuous. So basically, I redraw this. But there's a jump every time. Can't do that with this one, because this one's continuous everywhere, and it's always going up. So, in other words, as you draw this function from negative infinity left, to positive infinity right, you can never pick up your pencil and you're always going up, so you can't pull any of this. So, anyway, is everybody okay with this being a one-to-one function? So, everybody remember, when you first saw inverse functions like in pre-calculus, how did they tell you to figure out what the inverse function is? Swap y for x and solve for y, right? Can we do that? See what we have is y equal x 5 plus x 1. Want to know how to solve that? I tell you what, if you solve that for me, if you give me a closed form equation, at any time within the semester, do it right now, just slip it to me. You can walk out. It's best, bro. You can't write this in closed form equation. And I don't mean that mathematics is fun. It's been proved that you can't do it. It exists. It's got an inverse function. You just can't write it down in familiar terms. I can figure out where it is numerically. You say, hey, Jim, what's some point? I could figure out something, but to write it down in a formula close form, it's impossible. So this makes this question intriguing. Let g of x be the inverse function. This is one-to-one, so I know it exists. In fact, I could draw this thing. In fact, it's fairly easy to draw this. And then flip it over y equal x and what its inverse is. Find g prime of so if we use this previous theorem that says basically g prime of y0 is 1 over f prime of x0, where x0, y0 is on graph of x, that is to say f of x0 is y0. I want to use that. Well, for this problem here, g prime of 3 is 1 over f prime of x0. And I know what f prime is, right? F prime is pretty easy, right? All I have to do is, problem is I don't know what x0 is. Well, anybody. Now I told you you can't solve this in general, you can. But maybe for the specific value of 3, you might be able to do it also. Anybody see something that you can plug in for x0 that will give you And you did that one by trial and error, like you tried some easy stuff. And really, actually, the truth of the matter is that's what you got to do. Because actually solving this equation in general, if I had had two instead of three, you'd be in trouble. If I had had one, I think you'd be all right, because you plug in zero, right? I have three, plug in one, it works. Right. I could also get minus one by plugging in minus one. Things are easy to see. But here, if this were two, I think we kind of. So. Okay, he found a solution, right? Here's what bothers me. Okay, so Eli looked at that and said, X zero is one words. Correct, I agree with you. But here's the problem. What if he got the wrong solution? What if there's another number that you can plug in and it gives you three, and that's the correct one to use? Right? I mean, Eli got a solution. He's very clever, looked at it, figured it out, but how do you know that there's not two or three others? And maybe one of those is the ones that we need to plug in. But as it turns out, Eli's solutions. Somebody tell me why. By plugging in one, Eli found the place on the original function f where the y coordinate is 3. Agreed? He found the point where the y coordinate is 3. Why is there no other place on the function where the y coordinate is 3? Because what do we know about the function? It's one that, right? If there was another solution, you could pass a horizontal line through those two solutions. So the fact that it's 1-to-1. So we can now figure this out. So G prime of 3 is 1 over F prime of 1, which is 1 over 5 times 1 to the 4 plus 1 plus 6. Okay. Okay. I want to start talking about related rates. And there's very little explanation that goes into this, and I'm not trivializing related rates. It takes a lot of practice, right? But what I want to do is I want to go through some related rates problems and just kind of show you how to do this. These are problems where you're starting to actually, this is a very important section because all of you in here are engineers, you're scientists, you're going to have to use this. So this is where I think one of the places we start to really see how to use this. Example. I throw a rock a lake. Simple splash, drop the rock. And its diameter is decreasing at let's say 3 feet per second. How fast is area decreasing? When radius of circle is 10 feet. How fast circumference decrease? In the related rates section, almost uniformly, calculus is fairly easy. Right, most of the functions have it all. The art is really the algebra and the setting of these setup. Okay. So, in these problems, unless they're totally trivial, I highly recommend always draw a picture. Right? It may seem childish and all that. Draw a picture, label stuff. Label relevant things in this particular problem. And everybody's done this, right? You've all thrown a rock in the lake, right? And what happens? You have a circle of waves coming out. Nice perfect circle. So here's my, oh, and by the way, let me picture. Simple. Well, let's see, what do I need? I throw a rock into a lake, an expanding wave comes from the central splash. I didn't say it's a circle, but we want to say that. I don't ever want to try to trick you on this. Looks like I should play with diameter, doesn't it? There's something about diameter in here. Okay. Look at my beautiful picture. Okay, that helps me. Got this wave, it's coming out, diameter is increasing. Okay, here's a piece of information that's going to be. Diameter is increasing 3%. And I want to know how fast is the area increasing when the radius of the circle is 10. What should I label on? Anything else? What is this piece of information telling? The diameter is increasing at 3%. Every second that goes by, the diameter is bigger. But can you interpret that in terms of derivatives? Notice this is in feet per second. It's in a change in feet. It's the change in diameter. So I'm going to interpret the statement. Diameter increasing, the capital D T is 3 feet per second. That's what I read. Change in diameter with respect to time, 3 feet per second. I'm not big on units. This isn't a physics class, but I'm big on units in the following way. You can use them to help you. Those units right there tell me that's a change in diameter, or it's a change in some length with respect to time. Okay, and this may seem childish too, but quest. Number one, what is it asking? How fast is the area increasing? So that's a change in the area with respect to time. when what? You give me a different interpretation of that, might be useful, given the information. When the diameter equals, alternatively, when P is equal to 20. Agree? And what's the second quest? So, oops. I think it's, you know, it makes some silly, but I wrote you right. So here's the deal. I know the DBT, but I need a formula, maybe for A in terms of D, or maybe. By the way, let me ask you this. If the DBT is 3 feet/second, what's the RBT? What's 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 what relationship between diameter and radius? So you know, diameter, you're right, diameter is double radius. And so if you take a derivative of this, the dt is 2 r. But this is 6, or I'm sorry, this is 3. So if you solve for dr dt, it's exactly sort of what Mike, I think, you sort of intuitive thought about it, said it should happen. Right? But you can do it hardcore. Okay, so I want to know the ADT. I've got some information about the DDT, DRDT. Anybody give me a formula that relates area to either diameter or radius? Right. And what is that? What's your preferred? I know those. Okay. Lots of people have knowledge. Okay, so let's check this out. Now you have, this is what's called related rates. You've got, you want to find the ADT and you've got the RDT, so you need an equation that relates them. So take the derivative with respect to t. Treat these both like functions of t. This is the ADT. Don't forget the chain. What's the derivative of, well, the pi's there along for the ride. What's the derivative of 2r? Or related. It's 2r to the first power, but I'm not done. I've got to multiply derivative of r. Don't forget that step. Remember, I'm taking the derivative of second time. Change. Okay. This is what I want when R is 10. Oh, and what's the RDT? 3/2. So this is 2 times R. That specifies time. Let me write this down. equals 10, and dr dt is always 3/2. I get dA dt is 2 pi times 10 feet times 3/2 feet per second. And what do I get here? I get 30 pi square feet. So that is how fast the area is changing. Square feet per second. How about question number 2? Can somebody give me a formula for the circumference in terms of either diameter or radius? That's the thing. Circumference of the circle is radius diameter. What's the formula of that in terms of either the radius and the diameter? That familiar? It'll see how fast the circumference is changing. ddt this again. dc dt is 2 pi r. So it should be just a factor of 2 pi. So and the order is 3/2 per second. So I get 3 pi. We're going to spend, so what I want you all to do before Monday, I'm going to do one more of these. So I'm going to give you some instructions for Monday. Obviously, go over the previous section, make sure that you've got that down, the inverse treatment and all that. Then start doing those related rate problems. Do them. I've got a ton of them also up on my website, old test problems, things like that. Do those related rate problems because on Monday, this is the one that I think a lot of students have struggled with the most. Just it takes it. They're not particularly hard, and the calculus is usually easy. It's just you got to get your sea legs about set though. Anyway, do those exhaustively, and we're going to hit it hard on Monday. I'm going to give you another one that's good to think about. A person. So 6-foot person is walking away from a 20-foot street at in a straight line. Three. So 6-foot person walk away from 20-foot tall street line 3 feet per second. I've got 2 questions. Number 1, how fast is person shadow lengthening? When person is 100 feet wide. B, how fast is the tip of person shadow? Okay. This is another two-parter, and this calls for a picture. And I think everybody's experienced that. Have you ever been out at night, you know, and walking down the sidewalk, and you go under like a street light, and you're walking down, and you observe your shadow starts to grow away from you, right? This is what it's asking, right? So you walk under a street light, it's 20 feet tall, and you're 6 feet tall. So you look at your shadow, when you're 100 feet away from that light, how fast does your shadow lengthen? Because it lengthens, that's why it's tall. Like, when you're right under the light, almost no shadow, it starts growing, right? When you're 100 feet, how fast is it lengthening? And how fast is the tip of that shadow moving down the sidewalk? This calls a picture. There's the light pole. And here's the person. What a beautiful rendition of this. But remember, keep it simple. What can I label? What would be smart of me to label? The height of the person. Let me ask you this. Does the person's height change the problem going on? No, so I'm safe to. That's always a 6. That person's always a 2. Okay, that always 20 feet. No problem there. What else should I'll be like? Okay, right, but how am I gonna live fast? I'm gonna need distance. I'm gonna need distance of somewhere. I need a shadow too, don't I? So let's this. What does this represent here? That's your shadow, right? So I'm gonna call this S. And I'm gonna call this X. X is gonna be clear. X is going to be the person's distance from the street light, and S is going to be its shadow. Everybody okay with that? Notice I've got some things numbered and some things letters. A rule of thumb is this: if you label a quantity on your picture, if that quantity can change as the problem progresses, leave it as a letter. In fact, you're safer to call a number a letter than a letter a number, right? Because if there's something that's changing, you can call a number, that can burn you back. Okay, well, let's just see what we can get from this. A 6 foot tall person. You know what? I think I got that list. That's taking care of it. 20-foot street light in a straight line at 3 feet per second. What is that telling me? What's the 3 feet per second? It's how fast the person's walking. So let's look at our picture here. What is that symbol? The 3 feet per second is the person walking away from the pole. What is changing? What is the primary thing changing? X. The person walking is changing the X, right? And as a secondary thing, probably changes S too, but primarily X is changing. So how would we interpret this 3 feet per second? The change of X, how much I'm making grow X per unit time, that is 3 feet per second. I'm making X grow 3 feet every second. Now, that's all the information given. Then it starts asking a bunch of crap. So it says, what is my quest here? Number one, how fast is the person's shadow lengthening when the person is 100 feet from the light? What is this asking? My shadow lengthening, that's the change in my shadow. Change in shadow with respect to time. Right, that's the S&T. I want to know this. when? When I'm 100 feet from y. So that's when x is 100. Agree? How about the second? No, yeah, this. The tip of the shadow is how fast the whole base of the triangle is moving, right? So we're asking for the change in x plus s. The whole base of triangle. When x. Everybody okay with that? Yeah, because the tip of the shadow, how fast it's moving is how fast that base of the triangle is. Everybody okay? So. Okay. So. What do we know? Well, we know dx dt, and we want to know some stuff about the dt. So I guess what I need here is I need some kind of equation that relates x and s somehow. C by c. 4 by 2. Well, no, because we don't, so, right, you say, I guess it takes some 33 seconds and a third to get out to there. But, that's not quite going to work, because what we need is, we need I don't know, that's not going to show us how fast the shadows. Let me ask you, a lot of this stuff boils down to kind of stuff you might have seen in geometry. And a lot of, so here's what's going to boil down to a lot of this problem. Pythagoras' theorem, or more generally the law of cosines, right? The law of sine. Do the law of cosines of Pythagoras' theorem, or similar triangles. Now, I don't have a lot of information on the length of this. But I do see some similar triangles. You all see similar triangles here? Notice the triangle formed by this person in the shadow is similar to the entire. Everybody agree with that? So if I went S is to 6 as what? This is to 6 as what? S plus x is to it's actually so I can simplify this. S is the 3 as S plus X is 10. And so I can make this even easier. S over 3 minus S over 10 is X over 10. So it actually is going to be a bit of a payoff for me to up around this bit. So I get 7/30 S. It's equal to 1/10 X. My goodness, that worked out well. There's an equation that relates S and X. Okay. Now that I've got my equation that relates them, now I'll take a derivative. A derivative with respect to time, and I couldn't ask for that because it's terribly easy to do. The derivative of S is ds to t. Derivative of x is ds to t. And we're going to learn some physics about this, which might surprise you. Let's answer question 1. We want to know the SDT when x is 100. Well, the SDT is 37 times 1/10, which is 3/7 dx dt. Everybody agree with that? Let's just solve for the SDT. And what is the XDT? Is there anything that strikes you funny about this? Look back at what I asked you. I asked you, how fast is the tip of this person's shadow lengthening when they're 100 feet away? Where did being 100 feet away come into play? Where did I use that? You were right not to answer because I didn't. Everybody agree with that? Never. I mean, here it is, right? We got this equation that relates S and X. And I got the SDT. I know what the XDT is, so that gives me the SDT. I never had to use the fact that X was 100 feet. So somebody interpret that. What does that mean? As you walk down the sidewalk, watch your shadow lengthen. It's always lengthening at the same rate, no matter how far away you are from one. It's always increasing at exactly the same rate. Because this information is superfluous. Didn't matter. Didn't come in. Everybody okay with it? Quest 2 is now easy because we've done quest 1. Trying to find the change in the bottom part of the triangle, which is x plus s. And this is the xdt plus the sdt. And the xdt is 3 feet per second. And the xdt is 9/7 feet per second. And if you put it together, it doesn't matter, it's 30 over 7 feet per second. And this makes sense, doesn't it? Think about it this way. How fast is this triangle lengthening? It's how fast x is growing plus how fast s is growing. X is growing at a constant 3 feet per second. So it's x is growing, and we already found that the shadow is lengthening at 9/7 feet per second, so it's growing. So this makes sense to me that it's the sum of those two. Okay, any questions on that? All right, for the weekend, hit those homework problems hard, and now we will take the quiz.